Okay, so Pedro and Bobby each own an ant farm. Pedro starts with 100 ants and says his farm is growing exponentially at a rate of 15% per month. So we should have a memorized formula for that. The formula is our initial amount, 1 plus or minus r to the t over p. So Pedro, starting with 100 ants, it's growing at 15%, so plus 0.15 per month, so t over 1 month. Bobby starts with 350 and says his farm is steadily decreasing by 5 ants per month. Now, his is increasing by a rate, so that's definitely a percentage change, and so it's more of an L-type function as we have here. But when it's decreasing by a set amount, that's linear. So Bobby's formula is going to be more linear, and his final amount is going to equal his starting amount of 350, but he's losing 5 ants per t, where t is going to be our number of months. Okay, we had month here, so we can assume t is in months, and we're going to go with t is in months. So assuming both boys are accurate in describing their ant farm, after how many months will they both have approximately the same number? So we're looking for their final amounts to be the same. So we're going to take this and set it equal to this. We don't need that over 1 anymore. We got it. Now, we don't know how to solve this, unfortunately. It's an exponential on one side and a linear on the other. So we've got a t in the numerator, which normally, or a t in the exponent, which normally we can handle. To get it out, we would divide both sides by 100. We'd log both sides, but then we've got a t wrapped up in the other side. So the only way we can really do this is graphically. So I would go to my calculator, I would type in this linear function as one equation, this linear function as, or this exponential function as the other, and just find the point of intersection. So 100, parentheses 1 plus 0.15 raised to the x power, over 1 technically, but you don't have to have that obviously because it is 1. 350 minus 5x. Start with zoom 6, so my standard window, if it's not big enough, I'll change it. Yeah, I see nothing, okay, and that's because just even looking at our linear, our y-intercept is 350, and then it's decreasing. This one's y-intercept is 100, so if I'm only going up to 10, of course I'm not seeing anything. So I'm going to go from 0 to 350. Nope, not on my x. On my y's, I'm going to go from 0 to 350. My x is the number of months, so let's go from 0 months to, oh, I don't know, 24 months. We'll see it out 2 years and see what happens. And if I graph that, there's my exponential starting at 100 and increasing at a rate of 15%. And my linear should be coming starting at 350 and decreasing by a set linear amount of 5x. We want to find that. And again, this is our number of months. So second trace, option 5 intersect. First curve, right now my cursor is at 12,535, and it's on the first curve I typed in, so it's on this exponential. So I'm going to scroll left till I see my cursor. There it is. Okay, so get that near the point of intersection, hit enter. And then my cursor comes up on my second curve, my line, so if I scroll left and right, you'll see that tracing along the line. Again, bring that to the point of intersection, enter, enter, and 8. So after how many months? It's 8.08, so the nearest month is 8 months. So, and it says approximately, so we don't need to worry about the exact there, just the nearest whole number is 8. So it's interesting, that's an exponential question. This part is Algebra 2. This second part, writing a linear, is technically Algebra 1, but it's all, math is all inclusive. Once you learn it from Algebra 1, you know, there's free reign to use that. On number 17, we're asked, what is the solution, if any, of the equation given here? Now, this is a rational equation. We have to get a common denominator all the way across. Before doing so, though, let's factor this and see what it's really made of. This factors into x minus 4 and x plus 3. So we don't need to think about that anymore. Let's just get a common denominator. So the x plus 3 we already have in common here. This one definitely needs an x plus 3. Okay, now the x minus 4 and the 4 minus x are not technically the same thing. This order is a little odd for us. X minus 4 is what we like and what we're used to, seeing that x first. If we want to flip the order of this, though, we would need to, and it does need to be flipped because those are not the same factor right now, we need to multiply this one by negative 1 over negative 1. And that'll flip the order of this. So times negative 1 on the bottom times negative 1 on the top. So that, well, we'll get to that, but then this one, you can just give this one an x minus 4, because this one is an x minus 4, this one is about to become 1, and this one needs an x minus 4. So once you have a common denominator, x minus 4, x plus 3, this is an x minus 4, x plus 3 now, x minus 4, x plus 3. When you're solving, you can just drop it, and then the equation you now have to solve just comes from the numerator. So it's a 2 times an x minus 4, and then minus the negative 1 is actually going to turn that to plus 1, which we don't need because there's times that 3, x plus 3 equals 2x minus 2. And then we're just solving the linear equation. So 2x minus 8 plus 3x plus 9 after distribution. Combine like terms, 2x and 3x is 5x, negative 8 plus 9 is 1. And then get all our x's on both sides. So I'm going to subtract this 2x over. I'm going to subtract this 1 over. So I get 3x equals negative 3, and x equals negative 1. You always want to check it. Okay, you always want to check it and make sure that's not extraneous. Would negative 1 have made my original denominator 0? No. No, no. The only extraneous roots we could have gotten is if negative 3 had shown up as our answer, we would have had to have rejected it. And if 4 showed up as our answer, we would have had to have rejected it. But it didn't, and we're just at x equals negative 1. So solving a rational equation, pretty standard for Algebra 2. 2013, 1.6 million students took an SAT exam. The mean, the mode, and the standard deviation were calculated to be 496, 430, and 115 respectively. That means mean was 496, mode was 430, and this is our standard deviation. Okay, so the order they list the numbers in is the same as the order they listed the titles in, which is why they use that word respectively. Which interval reflects 95%? So 95% in stats we should know is 2 times the standard deviation. So, and it's always 2 times the standard deviation away from the mean. So the mean plus or minus the standard deviation. That gives us our 95% confidence interval, our margin of error interval, all of those things. So the mean is 496 plus or minus 2 times the standard deviation was 115. So it's 496 plus or minus 230. The mode was given to you for no reason other than to make you sift through what information is relevant and what's not. In 19, which statement regarding the graphs of the function below is untrue? So if you look at what we're talking about maximums, y-intercepts, end behavior, and rationals. So we should look at these on our calculators. F of x and j of x have a maximum y value of 3. Well, we'll type in f of x and j of x. F of x is 3 sine 2x. And j of x is the negative absolute values under your math button. So right here, your math button. And then if you go over to number, I think, you'll get absolute values, your first one. And so we'll type in 4x minus 2. And then plus 3 and delete the rest here. Okay, I probably should have cleared that all out from the start. So there's f of x and j of x. We're going to check and see what their maximum values are. Now, as far as the first function, they did give me an interval from negative pi to pi, so I want to limit my window from negative pi to pi. That's the only section I'm looking at. You're graphing a trig function, so your mode should be in radians, which, it's not, because someone used my calculator recently and put it in degrees. I would think most of yours would be in radians. And then your window for your y-axis, the 0 to 350 was that ants problem, so we want to change this, and we can go from negative 10 to 10 just to start, and we'll adjust if we need to. So f of x is going to be our sine function. Does this have a maximum y value of 3? Okay, they do. Clearly, they both have the same maximum. So here's the absolute value's maximum, and here's the sine graph's maximum. So if I do second trace and I look for that maximum value, I'm on my sine curve right now. So I'm looking for the left bound, so I'm going to keep my cursor to the left of the maximum, hit enter, and then scroll it to the right of the maximum, hit enter, and then guess, hit enter through that, and you'll see that your maximum value is 3. So this is true. They're looking for which one is untrue. So that one was true. F of x, h of x, and j of x have one y-intercept. Well, we have f and j on our graph. F only has one y-intercept right here at 0. J, the absolute value function, only has one y-intercept. So those two are true. We do need to look at h of x, which is log base 2 of x. So to type in a log to your calculator with a different base, you should probably just type in, it's a good time for the change of base formula, just type in the log of x over the log of 2. That's the same thing. That's our change of base formula, which reminds me I should throw that on a flashcard. So if I type in log of x divided by log of 2, it's going to give me that graph, and we just want to see if that has one y-intercept. Now that comes down and down and down. Does it ever actually hit the y-axis? I think I want to zoom in here. I'm going to zoom in, right, and bring my cursor right down to that where it looks like it hits, but it clearly doesn't cross. Zoom in there and see where my log graph comes down here. Yeah, this is not ever going to actually hit the y-axis, because we should know with our log parent graph that the y-axis is an asymptote. So it is not hitting the y-axis, and therefore this one is the one that's untrue. Okay? As far as just looking through the rest of these to review some topics, because, that's obviously important. Oh, shoot, I just crossed out. Well, they want to know g of x and j of x have the same end behavior as we go towards negative infinity. So if I type in g of x, and type in j of x, what is the end behavior as x goes towards negative infinity? So zoom 6. As we go towards negative infinity, this one's going towards negative infinity, and this one's going towards negative infinity. So as x approaches negative infinity, we're trying to trace our graph to the left. So for this polynomial function, it would go up, and as we go towards the left, this is going towards negative infinity. Same thing here. As we trace this one going towards the left, it also goes towards negative infinity. So that one is true. And then the last one says that g of x, h of x, and j of x have rational zeros. So if you, first of all, on g of x, your zeros are positive 0.5, negative 4, and 2. So certainly that has rational zeros, meaning zeros that are not repetitive long decimals. J of x, which is our absolute value function, that clearly has zeros at, it looks like, negative 1 and 1. And then the other graph that we would need to look at, and I'll clear this out, is h of x. So again, we're typing in that log function using the change of base formula. log of x divided by log of 2. And if I graph that, its root is 1. So, yes, that's a rational 0 as well. Okay, we may have one more. Time for one more before I got to cut this video and go to class. But number 20, when g of x is divided by x plus 4, the remainder is 0. So, hey, guess what? X plus 4 is a factor. And that means, by the remainder theorem, that not f, g, I guess is what they're, g of negative 4 should equal 0. So, which conclusion is true? And there it is. Okay, if that's the factor, that's our 0. Okay, g of 4 will not necessarily be 0. X minus 4 is not the factor, x plus 4 is. And that's obviously not true because we just said 2. Alright, do we have time for one more? Probably not. We have an average rate of change question, and we'll start with this one in the next video.